Greetings to Ms. Kerk. We are from Group E4 and today we're going to present our topic, which is application of logic on traffic light. And this is our group member. First is...
My name is RAFEESYA binti RIDZUAN.
Second is my name is FARAH NABILA binti RAHIM.
And my name is SYAKIR FAISAL bin SAMSUDIN. Introduction. Urban infrastructure cannot function properly without effective traffic management, and maintaining safe and efficient traffic patterns is essential to facilitating efficient transportation flows. The use of logic to control traffic light operation is the fundamental component of traffic control system. In order to understand how discrete mathematical principles influence the decision-making processes that govern vehicle and pedestrian movement at intersection, this project explores the complex relationship between logic and traffic light control. This study attempts to give a true understanding of how these mathematical ideas contribute the optimization of traffic flow and improve overall urban mobility by looking at the application of logic in traffic management.
Next, we're gonna go into the topic description. So, mathematic logic is when we study mathematics as a language by understanding mathematics sentence using the rules of logic. The rules of logic are applied to define the meaning of a mathematical statements. Statements are defined as declarative sentence that have a truth value, which is true or false, but not both true and false. And it is usually represented using variable like P, Q, and RS. As example, Segamat is a state in Malaysia. That is a statement because it has a truth value which is true. And however, what day is it is not a statement because it a question and doesn't have any truth value. So next we're gonna go into compound statement. Compound statement is a combination of multiple primary statement connected using logical connective. The statement truth value is displayed using truth table. By using truth table, statement truth value can be tested by applying the logical connective, and then in truth table we use T for true and also F for false values. And if the statement has two variables, then the truth table has 4 rows, which is 2T and 2T 2F and 1T 1F. And if the primary statement has 3 variables, then the truth table has 8 rows, which is 4T 4F, 2T 2F, and 1T 1F. Next, we're gonna go into the logical connective. First is negation. Negation gives an opposite truth value of the given statement. And negation of statement P is denoted by negation P, and it reads as not P. So as we can see in the truth table, P, the negation of P with truth value T, it is F, and for the negation of P for truth value F, it is T. And then next we're gonna go into the conjunction. Conjunction of a statement P and Q is denoted by P conjunction Q, and it reads as P and Q. And the rules for conjunction is, if any of P or Q is false, then P conjunction Q is false. And if any both P and Q is true, then P conjunction Q is true. So, as you can see from the truth table, if both P and Q is true, then that means that P conjunction Q is true. Next is disjunction. Multiple statement can be combined using OR to form a compound statement. Disjunction of statement P and Q is denoted by P disjunction Q, and it reads as P or Q. And if any of P or Q is true, then P conjunction Q is true. And if both P and Q is false, then P conjunction Q is false. So this, as we can see, that if there are any truth value, if there are any true, then this junction is true. And next is conditional. Conditional is multiple statement can be combined using if then to form a compound statement. In conditional, we combine the statement using if then. As you can see, conditional of statement P and Q is denoted by if P then Q, and it reads as if P then Q. If P is true, then Q is false. Then P conditional Q is false. Otherwise, P conditional Q is true. Lastly, biconditional. In biconditional, we can combine multiple statements using if and only if. Biconditional of statement P and Q is denoted by biconditional Q, and it reads as P if and only if Q. If both P and Q have the same truth value, then P biconditional Q is true. Otherwise, P biconditional Q is false. So in biconditional, the P and Q have to has the same value. For example, both P and Q has T, so that's mean true, and both P and Q is false. It is the same, so the biconditional is true, and otherwise it is false.
Next, I will be presenting about the concepts and applications we use in our project. First one is the concept we selected, which is statement and logical connective. Statement is a declarative sentence that can determine the truth value, either true or false. Statement is also a logical proposition that can only hold one value. We also uses logical connective, which is the symbol, to connect two or more statements. There are 5 symbols in total, which is and, or, not, if then, and also if only if. These compound statements can also determine the truth value based on the component statement. Therefore, we can express a complex idea and make logical inferences by using logical statement and logical connective. Next is the selected application we use, which is system specification. For example, when vehicle use road to move from one place to another, there will be interferences of vehicle and pedestrian with traffic lights and tolls. These traffic lights and tolls display different colored lights that hold different meanings. For example, red means stop, green means move, and yellow means preparation state between the color red and green. On the other hand, we also use proper and simple language sentences to guarantee better understanding and functionality of the system.
Let's go to the example. Example 1. In for junction array, if the north direction has a green light and south direction has a green light, then the east direction should have a red light and west direction should have a red light. So from the sentence, we can create the logical statement, which is if the north direction has a green light and south direction has a green light, then the east direction should have red light and west direction should have a red light. So the solution is we need to break the statement into a small part. So from the statement, we can create four small statement, which is P, Q, R, and S. So for the P is the north direction has a green light, Q the south direction has a green light, R the east direction should have a red light, and S the west direction should have a red light. So by the logical statement, we must create the logical expression, which is P and Q implies R and S. So when we have the logical expression, we must create the truth table. From the truth table, we can define that the statement are contingency because the 7 columns contains both true and false. And lastly, we can create the logical circuit, but before that, we must simplify the expression. First, we can use definition of implication. When P implies Q, it will be not P or Q. And then we use the De Morgan's law, and it will change the symbol N to O. So this is the circuit, which is O will use this symbol and N will use this symbol.
So next is example 2. The statement is, before entering the highway, road users will have to pay a certain amount of money at the toll, whether they are driving a two-wheel vehicle or a four-wheel vehicle using prepaid card of their own. You can see in the picture, there's vehicle and the toll. So, by this statement, we can create the logical statement, which is, if their card balance is sufficient, then they can pay the toll. If they can pay the toll, then they can continue their journey. Their card balance is sufficient and they can pay the toll. Therefore, they can continue their journey. So, given the following argument, we have to write the primary proposition, which is, first is, their card balance is sufficient as A, they can pay the toll as B, and they can continue their journey as C. So as we see here, I have write the primary proposition. Next, we need to write the proposition in symbolic form. So, the first one, I use if-then logical connective. The second one, I also use if-then logical connective. And the third premise, I use AND logical connective. So here, the first premise is A implies B. The second premise is B implies C. The third premise is A and B. And this is the conclusion, which is the proposition of C. So the conclusion is C. We need to prove that the argument is valid. So first, we have to write all of the premises, which is A implies B as premise 1, B implies C as premise 2, and A and B as premise 3. So by using the first and the second premise and applying the syllogism method, we can get A implies C. And by using the third statement and applying the simplification method, we can get A. Next, by using the fourth and the fifth statement in the table and applying the modus ponens method, we can get C. So after we have proved that the argument is valid, next we have to draw the logical circuit. So the first premise is A implies B, the second premise is B implies C, and the third premise is A and B. So, if we use this logical connective, we cannot draw the logical circuit. Therefore, we have to simplify the logical expression by using the definition of implication, where P implies Q will become not P or Q. Therefore, this logical expression will become not A or B and not B or C. And this logical expression will remain the same, A and B. So, this is the logical circuit of the example 2, where here shows that C is the conclusion of premise 1, 2, and 3.
Lastly is example 3. This traffic light has pedestrian traffic signal that allows pedestrian and road traffic to use the road alternately. When pedestrian light changes to green, this signal pedestrian to cross the road. So when this light changes to green, and then the pedestrian after that changes to green, then pedestrian can cross the road. These are the logical statement. The crossing button is pushed or pedestrian signal changes to green and pedestrian can cross the road. The crossing button is pushed or pedestrian signal changes to green and the crossing button is pushed or pedestrian can cross the road. So are the statement given logically equivalent? So in this example, we're gonna prove whether the statement given are logically equivalent or not. So from this logical statement, we're gonna identify the statement, which is first is statement 1. The crossing button is pushed or pedestrian signal changes to green and pedestrian can cross the road. And then the next statement is the crossing button is pushed or the pedestrian signal changes to green and the crossing button is pushed or pedestrian can cross the road. From the statement that we have identified, we can break it into small parts by using variables P, Q and R. So the crossing button is pushed is P, or the pedestrian signal changes to green is Q. Pedestrian can cross the road is R. For the next statement is the crossing button is push, which is P, or pedestrian signal changes to green Q, and the crossing button is push, which is P, or pedestrian can cross the road, which is R. We can form the logical expression. So the method that we have chosen to prove whether the statement is logically equivalent is by using the truth table. So by using truth table, the column for both of the statement have to be identical of each other. These are the logic circuit of example 3. As we so for OR, we're gonna have to use this, and for AND, we're gonna have to use this. It's OR and it's not AND. So for the first statement, which is P, or Q and R, which is so P or Q and R is logically equivalent to P or N, Q or R. So these are the logic circuit.
For the conclusion, in this comprehensive project, we delve into the practical application of logic within the design and operation of a traffic light control system. The exploration initiates with insightful introduction to logical reasoning, laying the groundwork for a thorough analysis of the specific algorithm and decision-making procedure that govern the timing of traffic lights. The investigation extends into the complexities inherent in prioritizing diverse forms of transportation, adapting to dynamic traffic conditions, and effectively coordinating the synchronized operation of multiple traffic lights at intersection. Through this endeavor, we aim to unravel the nuance intricacies of traffic light control, offering a holistic understanding of how logical frameworks play a pivotal role in enhancing efficiency, safety and traffic flow in urban environment.
That's all from us. Thank you.